Log on, tune in, find out. Another good idea from Cambridge.
I'm very happy that I could find three excellent speakers for this session, and I hope you'll enjoy it. The first speaker is Nancy Flournoy, and she'll talk about some issues in response adaptive designs for dose finding studies.
Thank you, Stephanie. And thanks again to the organizers for a wonderful week. I have to say that I came, I had a talk prepared, and then I forget whether it was early this week or early last week, France equated the 3+3 with the up and down, and I thought I had no intention of saying anything about the up and down, but I threw out my talk and I rewrote another one, and so here we are. It also forced me to look at some things that I'd gathered that were new sort of over this last year that I hadn't looked at before and been meaning to put them together. So a lot of what I have is sort of cribbed from other people, and you'll see I tried to give appropriate attributions. So this figure is courtesy of Val Fedorov, and it shows the basic context in which I'm going to talk. I'm talking really simple, at least the first half is really simple. The second half gets complex. So we have the standard dose response setting. The first part of my talk, we're just going to concern ourselves with monotonic increasing curves, which we can refer to as the probability of toxicity. And then later we'll look at the some designs concerning efficacy without toxicity. So that's my setup. And the first thing I want to do is make the point that the 3+3 is not the up and down. And then we'll talk about treatment allocations and particularly look at the CRM and the up and down. There's some new results on best intention designs, of which the CRM is a special case. And so I will tell you what I think I've learned about those new results. And then I will, so this is in the toxicity response situation, and then I'll move to the efficacy and toxicity response situation and talk about best intention designs and optimal designs. So, okay, so here, this slide says it all. The 3+3 is not the up and down. And why is that? Because the 3+3 goes up. There is no down in the 3+3. It is an escalation procedure. The up and down, on the other hand, goes up and down. So if you're at dose K, you can go up one step, you can go down one step, or you can stay put. So if you take the CRM, for example, and you add the Goodman restriction that you can only go one dose at a time, it is an up and down design. So the distinction is usually not whether it's an up and down design or not, because once you get into these kinds of clinical settings, you're usually forced into an up and down situation by the physicians. And a more meaningful distinction is short memory versus long memory. So, just to kind of put the, sort of an end picture first, to put in some context, this is just one set of information that's abstracted from some recent work by Oren and Hoff that compare the proportion of correct selection from the correct selection of the MTD by the CRM and a group up and down that has a cohort of size 2. And I'll explain more about what that is in a minute. But the point here is, they had a bunch of scenarios, and each scenario, the MTD was at a different dose level. And then they looked at the ability of the CRM to pick out the dose that was closest to the MTD and the percent of time with which that happened. And with the CRM, of course, it's the last dose that predicts the MTD. In the up and down, the procedure does not attempt to converge to a point, it converges to a distribution, and so the recommendation is to use isotonic regression then to estimate your point, and we have a series of results there. And this is after 8 cohorts. They looked after 16 cohorts. The numbers get a little better, but not much. And so I heard someone else say in a different context, I guess it was, the argument really isn't between the CRM and the up and down. The argument is if I'm going to try and use one of these procedures to recommend the single next dose to go forward with to a drug company, you've got to be out of your mind. None of these are good enough. So, what I would say is, where is the place for these designs? They're used a lot. But the place is to get you in the right ballpark. So they're like startup rules for something else. They're like, we're going to somebody was talking about, we're going to start out by committing just a few resources, and then as we learn more, we'll commit more and more resources. Well, these are procedures that are going to, sort of tell you where you ought to be looking. But in the best case here is less than 60% chance that in fact you did recommend the right dose, which means 40% of the time you were wrong. And if I was recommending something to a drug company, I wouldn't make the recommendation that they go forward with just one dose from there on. So, just a little quick tutorial on the theory of up and down designs. We have, and these figures are courtesy of my husband Len, who programmed them yesterday for us. Some nice simple little curves here. This is the probability of toxicity. So let's just assume that every time you see a toxic response, you're going to go down one step. In that case, you can think of this in the Markov chain situation as the transition probability. If you're going to go down if there is a toxicity, then not only is this the probability of toxicity, but at any particular place that you happen to treat a subject, it's the probability that you're going to go down. And then we take 1 minus that, and if you have the simple little rule that you're going to go up if there's no toxicity, then 1 minus this curve is the probability, the transition probability that you're going to go up. And for the random walks, the asymptotic treatment distribution is very well worked out, and things converge the treatments will converge exponentially fast to the treatment allocation probability. And so when one talks about asymptotics, a sample size of 24 is more than enough, even if you start a long way from the target. So what Durham realized in one setting, and Steve Durham and I examined to a greater extent, and realized in this case, is that if you do this little rule, the treatment allocations are going to be clustered around the point where these two curves cross. So in this case, notice this happens to be the LD50, which is why for a long time, people knew that the basic little up and down worked well to estimate the LD50 and didn't work well for anything else, and that's because the treatment distribution ends up right in this area. So if you don't want to be in that area, maybe you want to be over here at 30%, well, you have to shift the probability that you're going to go down. And so if you take this curve and bias it, see now it crosses at the 30% mark. And how did we bias it? We took the target probability of toxicity and divided it by 1 minus the probability of toxicity, and that does it. And so this observation, as there are many ways you can bias the curve to get a curve that will cross at this point, but one of them would be to flip a coin, where now the probability of going up will be no toxicity, and you flip a coin with this probability. And so if you do that, your treatment distribution is going to cluster around the point where these two curves cross. So the treatment distribution clusters around the point where the probability of going up equals the probability of going down. So this should be a histogram of points, but this little schematic gives you the idea that it's unimodal, it's high at this point, and the spread will be determined by the slope of the curve, and the step size of whatever your up and down, whatever your dose step size is between interval between the doses. So now Luke used a different up and down design in the case of efficacy and no toxicity. He said he as a starting rule, he used the procedure: you're going to go down if there's toxicity, you're going to go up if there's no toxicity. Well, the same theory works. You consider these are the probability of these events then form the transition probabilities, and the allocations are going to cluster where the probability of no toxicity is equal to the probability of efficacy. And that is not the same point as the dose that maximizes the probability of no toxicity and efficacy. So this procedure sounds good, but it does not cluster the points under the target that you're seeking. And that's a simple corollary of the theorem that we had. So what to do in this case, there's not a good answer. I mean, there is not a good up and down for the toxicity efficacy situation. One that works but is not clinically appealing is just to discretize the Kiefer-Wolfowitz procedure. And it's described here, you don't need to read it. It basically says you treat patients in pairs, and if you have a failure here and a success here, you move this way, and if you have a failure here and a success here, you move this way, and if the two responses are the same, you don't do anything, or you can flip a coin, and that procedure will cluster the treatments around the best dose. But it's clinically unappealing because you don't distinguish between did you get a failure from the toxicity or a failure from no efficacy. And try as we could, we were not able to think of a way to introduce to use the failure information without destroying the property that it goes where you want it to go. So that's that. Okay, so let's look at the allocations now from the up and down in the MTD. This is from work of Oren, Ashraf Oren, and he showed this slide in Stanford this summer. And what we have here are the, I wrote it at the top, good, because I couldn't see it either. Number of cohorts allocated to the MTD. And we have the series of different scenarios on the left. We have the CRM, different scenarios on the rows. The CRM is on the left, the up and down is on the right. And so when you see all these papers that get published on the CRM and similar methods, what is typically reported is the average, which is where the line is here. So the considered to be good is how many subjects do you actually put on the MTD. And as you see, the distribution of cohorts, the distribution of the number of cohorts placed at the MTD in every case here for the CRM is much wider than for the up and down. So I give that to you to chew on. I may be going too fast. No? Okay. So best intention designs now. Best intention, this term was coined by Val, which can refer to Bayesian or frequentist methods. It doesn't matter. There's a lot of them out there, where the basic procedure is you estimate the place you want to go and you put your next treatment at that point. So best intention. So this is a result from a recent dissertation Azrael from Tel Aviv, and he calls it the impossibility theorem. And so DJ is the MTD, and we have our doses that depend on the past, and we have our response that depends on the past, and it's Bernoulli, and it's some function of the data, and F is an increasing function, any increasing function. So we have a design, sequence of treatments, and then we have a sequence of estimators, which we call the MTD hat. Okay. So he calls that sequence of estimators strongly consistent with respect to a particular design if the estimators converge to the MTD for all increasing functions F. And then he says that in more probabilistic terms, because we have discreteness, we can formulate it, as I say, in more probabilistic terms. His conclusion is that under this framework, there exists no design, Bayesian, frequentist, whatever, there exists no design that satisfies for all increasing functions F that the design will converge to the MTD, regardless of how large n is, with probability 1. What
is F there?
F is any increasing function, all increasing functions F.
And where is participating in your formulation?
Because
I didn't give you the proof.
It means there's monotonicity, right?
Yeah, it's for any monotone increasing.
Oh, the dose
It
response.
just means
Yeah,
the
yeah.
monotonicity of the dose response.
Yeah, the dose response.
but it's not closed class.
So, but all increasing functions is a big, maybe that's too much to ask. So,
It should be some condition of continuity, because I take this one and you never find
well, you can look at the proof.
the concept. Thank you.
Not my proof. Okay, so the next thing Azrael did, Chung and Chappell have some conjectures for conditions for consistency. And actually, Quigley and Shen had some conditions, but they were determined to be very restrictive. And so Chung and Chappell had some more lenient conditions that were just conjectured and not proved until just now. And so Azrael proved that if Chung and Chappell's conditions hold, then the CRM is in fact consistent. And so I met with, after Chung's talk this week, I talked to him, and he was talking about how to construct priors. And he didn't say it in his talk, but what he told me afterwards was that he was providing rules for constructing priors that would so you'd end up with a prior that satisfied his conditions.
For clarification, but this slide contradicts the previous one.
No, the previous one had to do with all functions. Now we're saying we're going to look at a subclass of functions.
Put some condition on the
But can we read once more? So previous slide.
Okay, now this one I tried to quote verbatim out of
For all increasing.
all increasing functions.
Okay.
Okay, all increasing functions.
Thank you.
Okay. So now we say, okay, we're not going to look at all increasing functions. His new proof. We're going that in fact, if you have functions that meet the conditions, then you will get consistency, and Chung constructs priors that satisfy the conditions. So I don't know if the priors satisfy the conditions, will the original function satisfy the conditions, but at any rate, this is a very big step forward if you're going to use the CRM and you want a result that's going to go to the
So is the consistency then conditional on given a particular F from this prior? You get
well, I will not claim to understand this completely. Okay, these are brand. Oh, he's in the back. He can
Is it a
help.
good time to jump in, or should I?
Yeah, jump in.
So there's actually no contradiction between this and what David just proved. And what David's proved is that there's no one single method that works perfectly under all possible scenarios. So the way that I've been doing is that, so the condition we set up is for any given dose response function, we can enumerate the f under which that function will be consistent. And then we will, based on that, to choose the f the dose response function that is consistent under the biggest set of f. So that's the idea of the calibration.
Okay, so what it doesn't tell you though is whether the F that's out there in the real world that's running the experiment belongs to this class or not. But even so, I think you know, there's
Another clarification. Is it this function if it's true dose response, or in this CRM they use this function which like approximation, local approximation? Which functions we are talking about?
Also, the condition is an interaction of the true function and the model that we use. And so one problem in checking consistency condition for the CRM is that you need to know, like for any given truth, you can tell whether this model satisfies the condition. But the problem is that you don't know the truth in practice, in real life, right? So what I've been doing is that I fix the model, which is what we assume. And then based on, for that given model, I can enumerate which f's under which that the model will be consistent. And then I choose a model so that the set of f is biggest. So that's the idea of the calibration.
So there's still some issues of model misspecification.
Right.
But before this theorem came out, we had these observations. That is, Oren and colleagues had a sampling scheme from a bunch of generated dose-response functions. And they found that Chung's conditions were met 26% of the time. Azrael actually sampled from the power function prior that is commonly used in the CRM execution, and found the conditions were satisfied 43% of the time. So, I mean, I think these are new results, and you know, they're going to take some time to figure out, as I say, how do you use this information, but it's interesting. So anybody else?
We just didn't give definition of the time. We said net 26% of the time. Which one?
So you're
Of
not,
all the things he sampled, 26% of them met the conditions.
you're not going too fast now.
I'm not going too fast now.
As you end that side of the question, are you going to answer that question, or are we meant to try and answer it?
I don't know. I just came up with the question.
But I mean, just to comment on that, it does strike me that
Well, I mean, this is a possibility, is to think about what Chung's done.
isn't there something obvious? If you take a Bayesian approach, anything that settles onto a single dose and stays there forever, your posterior distribution is not going to.
But it goes to the wrong place.
It may be the right place, it may be the wrong place.
No, I mean,
But your posterior distribution will not move to be towards 1 once you fix that point, because you need to be comparing that with something else. So if you had a Bayesian idea of consistency, I don't think there'll be any examples that satisfied it. Who's a Bayesian? Who can tell me that? Peter.
I mean, there is a true dose that it either converges to or doesn't. What's it got to do with being Bayesian?
Basically, always can do what you need.
You got to keep.
Okay, so in Azrael's paper, he does identify some designs in the literature that are consistent for the MTD. And where is Anastasia?
She left.
She went Ponte.
She knew that you are going to talk.
And I came back from lunch to put these references in here.
Move on, please.
Skip the slide.
So, as I say, these papers are new, and so what Azrael claims is that there are estimators based on isotonic regression that are consistent, and they include 2 by Ivanova and then 1 that they propose themselves. I put question marks here because I think his reference may not be correct. I don't remember an isotonic estimator in that paper, so maybe he got the reference wrong. But at any rate, there are some consistent estimators in the literature, and then the one that they propose is actually, I hear from Luke, very close to what he's been doing in the dose efficacy situation. And I didn't take time to write it down. I didn't have time to copy what his procedure is, but it does give some randomness to, so you don't actually, if you're settling on a point, you don't settle there with probability 1. You have some random movement in the adjacent points, and then your estimator converges, and that seems to be necessary.
Is the as-real paper published now?
Well, I'm referring to like 3 different papers, 2 of which are published and 1 is a preprint, I think. I got it at the end. I got the references down as well as I could. Certainly this proof paper is, I'll misquote, I don't know. Okay, so let's think back again about the big picture a little bit more. So what kind of trade-offs are we talking about in these designs? Well, in the case of an increasing response function, optimal design-wise, if you're trying to minimize the variance of your estimator, it would tell you to put all the points at the answer, which of course you can't do because you don't know the point, but that is a good, it sort of makes it logical that you would try to get all your design points at the MTD, say. And this is true except if the target is a quantile that's very extreme, and then the optimal design may be 2 points. But
that is true only for logistic regression.
No, that's true
If you
for.
have a more sophisticated model, that's not true.
I'm talking about your
Yeah,
sigmoid.
but let's say it's a 4-parameter logistic.
Well, let's stay with 2 parameters.
Oh, so you have to say.
Yeah, okay, 2 parameters. I'm sorry. When I said simple at the beginning, I meant 2 parameters. 2 parameters. The recording device has that. Okay. So this suggests that we want that a good design would converge quickly to the target dose. So what do you give up by that? If you converge quickly to the target dose, then you lose information about the slope of the toxicity function at the target. That's one thing. And the second thing is that if you converge too quickly, you can the procedure converges before you've actually gotten to the target. And this is a paper by Chang and Ying in the Annals that came at this problem from a educational item response point of view, but they were also dealing with the logistic function. They were doing maximum likelihood best intention design, just fit the maximum likelihood estimates and converge. But what they do is they actually calculate the cases in which the maximum likelihood estimate won't exist, and you will in fact converge before you've gotten where you're going. And the problem with these best intention designs is not that they don't converge, but they may not converge to the right place. And so what you see is this string of responses that don't change. And so you have a procedure that looks like it's got the answer when it may not. And so I think that's something you have to worry about.
Are you still ahead of time?
I don't know. I got 15 minutes.
Or does it matter?
No, I don't care. I mean, this is all sort of new material.
I combine these different paragraphs here. I mean, isn't the first one the kind of thing that Luke was talking about and saying that it wouldn't converge? Is there something that's going on that I don't?
No. Here I'm not talking about convergence now. I'm just saying this first paragraph just has to do with locally optimal design.
Yes.
If you want to know what the best thing to do is, it says put all the points at that point. And that gives you the idea.
Oh, I'm
that
sorry.
you-
Yes, I'm sorry. Yes, no, that's fine.
That gives you the idea that you should go quickly to that dose.
Yes.
And then the last two
Yes,
have to
well,
do
so
with
the-
why that might not be the best thing
yes,
to
I'm
do.
sorry. Yes, that's fine.
And in this one, the question is, do you want to know something around that point? Which gets us back to that first slide I showed where under the best scenario, the MTD is selected less than 60% of the time, which might say that dose selection isn't what we want to be doing with these little designs. That actually having information around the point instead of at the point may be a better utility function given what they really can do for us. And so other things that are well known is if you have a long memory design, whether it be maximum likelihood based or Bayesian, the first dose is very influential or even the first couple doses. The responses to the first couple doses are very influential on the convergence rate. And this was known for a long time with stochastic approximation, and it was recently rediscovered in this 2008 paper, but they attributed it to something else, but it seemed to be the same story. I already said that. And so then you have the alternative, which is to use an up and alternative, given you're in this little tiny framework of using an up and down design, which has short memory, but their finite operating characteristics are well known and analytic, and at least they're going to go to wherever they go fairly quickly, and then you can say, I've got all I can get out of this design, let's go do something else, because there won't be any more reason to stay there. Okay, now best intention designs for efficacy and toxicity. And so these are a few pictures courtesy of Val. And I'm not going to talk about the details behind the generation of these pictures because we have the generator right here. And I didn't want to get bogged down in too many details, but these are just some sample curves. Here, their sample size, there's 10 trials. And Val calls them a first order model, which means that you've got a line and you're trying to estimate some point on that line. So it's the basic dose response problem simplified as much as you can, and that we don't have a nonlinear problem. And what Val's been doing is going back into the old literature and trying to find out what people knew a long time ago about convergence for these types of best intention procedures. And so here we have dichotomous.
One is continuous and
The one's continuous, the other's dichotomous, but you see that they vary a lot at the beginning, and then they don't totally plateau out, but they don't change a lot. Here we're going out to sample sizes of 400, and that's certainly.
There is two attractors on 1 and -1. On this plot, it's difficult to see.
Yeah, that's going to show up in the next plot. I'll show you.
Don't you really have 30 patients in these things or something? Is that?
30 patients with 16 parameters, or 8 parameters?
No, I mean,
Yeah, 30 can be large, actually.
yes, okay, so, all right, that's fine, yes, so.
Well, it depends. Okay, so if you go to oncology, which is some background, then you're talking about these very small trials. If you go to cardiology, which is the background that Val had at GlaxoSmithKline, 400 was not big.
For dose ranging.
Yeah, so, again, one needs to have a toolkit that's very big because the scenarios out there that you have to deal with are that may come up are very big. And, one thing is not going to be right for all purposes. So I'm going to tell you what's here because I know you can't see it, but again, you're looking at how wide these distributions are. And on the left, we have adaptive Robbins-Monroe, which is an old procedure. And then on the right, we have de-optimality. And what is plotted is the distribution of the predicted dose. And Sample size is 100 and 400 in each case, and of course, okay, on the left we've got the adaptive Robbins-Monroe, and you look at the very nice peak in the middle of how often you're getting, the end dose is converging here in some sense to the dose you're looking for. Whereas here you've got this distribution around the points. But this distribution is much tighter than these distributions, and the thing that Val was referring to here is on the ends, you've got these little lumps of mass. He was calling them attractors. And this recognition that these attractors were out there goes back to older papers by Lai and others. So it's these points that are really the most disturbing. That is, there's positive probability that, again, that you don't converge, that you're out there on the edge, and those points get smaller as the curve, as you have a larger initial sample size, but they don't go away. Do you want to say something?
Yeah, I can add something. Another troubling fact here, or really strange fact, that compare 100 and 400 distribution. They are almost indistinguishable. So adding now additional observations when you use this adaptive Robbins-Monroe procedure, which can stand for CRM or similar stuff, that there is, you see, after some time you stabilize and you do not go anywhere in the sense, both in the sense of precision or convergence to something. You just stay there. While, say, for the optimal or whatever designs, some normal designs, you can see usual statistical picture, more observation, more precise answer you have.
But we're seeing the state that you're in at the very end. So are you actually stuck in one state, or are you moving up and down all the time, and it just happens which one we see?
These are the estimators. There's no up and down here.
But what is the estimator? Isn't it? I think you said it was where you were at.
Well, for
iteration 400.
the adaptive Robbins-Monroe, it's where you are. For D-optimal design, you estimate the point.
So that's what I'm saying. In Robbins-Monroe, you're constantly moving up and down. So if you take your estimator to be where you are at time 400,
Adaptive Robbins-Monroe is the following. I give you the definition. It was term coined by Jeff Wu. So you have a model. You estimate parameters, plug it in model, and then you moved where this curve intercepts something with the zero derivative, and you can show that it's actually coincide to the case when in Robbins-Monroe procedure you select each time optimal alpha. Sorry.
I'm just bringing you the microphone.
So it's plug-in procedure.
There are microphones. You don't need.
Oh, okay. Okay.
So there's this plug-in procedure, and it's exactly what they do in CRM and many others. So
What they
call
consider
best
it,
intention.
one of the things that makes it adaptive is you have to estimate the slope parameter as you go on. And so Jeff Wu considered the adaptive to mean the re-estimation of the slope parameter.
but there's nothing built in, or is there anything built in that says over time you try and make it more tight?
Okay, let us.
Well,
And they hit
the adaptive Robbins-Monroe is a best intentioned design in that you're putting the points where you think the answer is.
So because your estimates are getting better, it should get tighter.
If you the asymptotic theory under proper conditions will say that you get tight. Now, one of the reasons I think that might not be happening is because the asymptotic theory tends to be based on the Taylor series expansion. And to get consistency, you say you've got theta hat close to theta. And if you start out poorly in your initial samples, then theta hat may not be close to theta, and then you don't have any guarantees as to what's going to happen. Another thing that slows down the convergence is just in these likelihood-based methods, every time you add a subject, that subject adds relatively less to the likelihood. And so each subject has a smaller and smaller chance of influencing what's going on.
Okay, let's
Okay, so
get on with the talk.
yeah, no, we're getting there. This is not, okay. I mean, now I've just got some wrap-up slides that actually came from the talk I originally prepared. You know, I talked about how in phase 1 trials, inference and patient gain objectives complement each other. Well, I mean, you know, you want to go to the target, and minimizing the variance of that estimator tells you to put your subjects there. But in your 2-phase design studies, this isn't true, and I don't know that it's appreciated so much, that your inference and your patient gain objectives contradict each other. And that is, there is a number of models for efficacy and toxicity, bivariate models, for which people have found the optimal designs for estimating the dose that has maximum probability of success without toxicity. And so far, there are no 1-point designs that have been found. There are 2, 3, 4-point designs, and they are not at the maximum. So if your goal is estimation, you do not, you know, then your utility function is not to put your points there. And if you want to do the best thing for the patient, your utility function would be to put the points there. And so we have a conflict, which is then, I just listed the papers that have solved the problem that show there's a conflict, and then some ways to deal with it. You can penalize, you can use a compound criteria, you can penalize things, as Dragelin et al. Have done, and as Frasanto have done. So there are ways around it, but the main thing to do is to recognize that you have this conflict and to deal with the different objectives in some way. So.
Can you put the reference
Quite
slide?
a lot of discussion already, but there's
You
still
want to
time
look
for
at your name?
questions.
I got it. What reference do you want?
No, the first page. Yes, thank you.
So I have copies of this. I have copies of this for anyone who wants. I can send that to anybody who wants it. And I have copies of that one too. And I think that's just easy to find on the web.
I wanted to say something. Yes, there is this conflict between, you said, inference and patient gain, which reflects, it seems to me, in the fact whether you want your maximum, your estimates to converge quickly, or you want your design to converge quickly. Now, most of these designs are asymptotically normal. And this is a problem because it means the convergence is slow. You can do something by improving the asymptotic variance, but I don't think it's enough. You get a little bit better, but not much. So what we really want is a design which is not asymptotically normal. And so Markovian designs, under this point of view, are bad. Can we do something which converges quickly? I don't know, but I remember that Nancy's paper originally was called the bias coin design. So for efference type bias coin, yes, we can. We can do it. We can make it converge very, very fast. So maybe instead of 2 treatments, instead of 2 levels, we have more levels. We can extend that idea, perhaps.
And one thing I meant to say is that Sandra has generalized everything that I talked about in many different ways. And her references to her are here in the thing, in the paper. So if you want generalizations, look for her papers. I'm looking. You're up next, right? I'm looking for your. Oh, Bill's up next.
Question.
Yes.
I guess I was hoping you'd still have your slides, but an earlier slide you had a comparison, and one method gave 33% correct, another 29, and they were sort of vaguely comparable. So when it was 16 patients, I mean, those are probably about as good as you could ever do with that number of patients for those settings. So I mean,
Well, that's part of the point.
so I guess my question is there some limit you could? I mean, they may be doing okay.
Well, no, because
relative to what they might be able to
they
do.
looked at twice as many cohorts, and things don't get that much better.
Show that.
Yeah, I didn't show that. I didn't want to clutter up, too many things. But in this paper, they show it. They don't, everything gets better by a few percentage points. They don't get twice as good.
I guess my point was maybe there isn't a great method out there. You're doing all these methods are doing about as well as you expect.
Well, that was
from
my
this
point.
thing.
And my point was two. One is they're comparable, and the other is that we can't, you can't expect too much from a small sample sequential study. And I certainly wouldn't, try and sell one of these as determining the drug that you should, in isolation, take forward to some next step. The next step needs to have more exploration in it and some more dose finding. That was my point.
Anthony, last
Do we have
question.
time for any more?
If it's a short
You
one.
can ask while Bill's coming up.
Yeah.
Okay, is Peter Tarl still here?
No.
He gave a very entertaining talk yesterday on what I think is just a very could be thought of as a very complicated example of the kind of things you're talking about.
Exactly.
Yeah, okay. So what he was saying might perfectly well suffer from all these kind of problems. Is that your guess?
Well, I mean, he had enough complexity in there that I would not want to venture a guess, but I think. but I mean, that's part of what, some people are trying to do is to understand the simple questions so we can understand whether there are really problems for the more complex
So
ones.
it's just this.
Thank you.
You need to steal the mic.